This is premise class number 59, and today we're looking at sub-boundary layer vortex generators. They're also known sometimes as micro-vortex generators. And vortex generators are very interesting because you can find them in many different applications. They range from cars to aircraft, fixed wing and rotational rotary wings to wind turbines and so on. And there are so many different types of vortex generators and from different heights and shapes and different angles of attack, etc. And we're going to look at some of these today. So to do that, we're going to look at a paper called Computational Modeling of Three Different Sub-Boundary Layer Vortex Generators on a Flat Plate. This is open access, and you can find a link to it in the description. And quickly, let's talk about what sub-boundary layer vortex generators are. So to begin with, when vortex generators first came about, they've been around for like 50 or 60 years. When they first came about, they were typical vortex generators, so they were about the same height as the boundary layer. And one of the general thinkings behind this sizing was that we want to have them interact with the boundary layer, and I'll get into how they do that in a second, but we want them to interact with the boundary layer, so we should make them about the same size as the boundary layer. And then over years, they started looking at different sizes, and sub-boundary layer or micro-vortex generators have become quite popular as well because they have a lot of advantages, which we'll also talk about soon. So let's talk about vortex generators first, how they operate. The general principle of a vortex generator is that they generate vortices. Surprise. And these vortices, what they do is that their aim is to inject higher momentum flow into the boundary layer near the surface. Now, why would you want to do this? The main reason why you want to do this is to prevent stall. So if you look at how stall occurs, if you have the flow going over, let's say, a wing, this is a quintessential example, there's an adverse pressure gradient that occurs over the wing. So what that does is it decelerates the boundary layer because you have this pressure which is constantly pushing against the boundary layer once it starts to get past about 25% chord mark, which is for typical NACA 4-digit airfoil. For other airfoils, it changes the position when you have this adverse pressure gradient starting. But let's just assume a simple example first of all. So for a simple 4-digit NACA airfoil, the adverse pressure gradient starts at about the 25% chord mark. So you've gone over the wing a little bit. And you have this constant pressure continually just trying to decelerate the boundary layer. And that's not a big problem for the upper in the boundary layer because when you get higher up in the boundary layer, the velocity is faster. So this velocity, it will reduce, but it won't start to reverse. But when you get closer to the boundary layer, closer to the boundary, sorry, the boundary layer becomes very slow. Now, if you haven't seen what a boundary layer profile looks like before, it looks very like, imagine a exponential curve, like that's where it just starts off fairly slow and then it really ramps up and goes higher. So that's what a boundary layer profile looks like. That what this means is that as you go higher up in the boundary layer, the velocity increases, but very close to the boundary, the velocity is very slow. So when you're going over the airfoil, for example, you'll start to reach a zero velocity and then reverse. When that happens, you get. So the idea of vortex generators is, well, if we're lacking energy in this region and creating stall, then why not just inject some more energy there? And there are a whole bunch of ways that you can do that. One of them is with vortex generators. So you create vortices. These vortices spin around the inside the boundary layer. They pull higher moving, faster moving fluid or high momentum flow as the typical term you use is, and it pushes it into the boundary layer near the surface. That then like re-energizes the boundary layer there and allows the boundary layer to travel further over the surface before you then get this flow separation occurring before the velocity goes to zero because you've now given it more energy. And it reminds me of that Arnold Schwarzenegger song by Luke Millions. Anyway, it gives it more energy and it prevents stall. So you can push the airfoil, for example, to much higher angles of attack and still produce a lot of lift. So that's how vortex generators first came about. And as I mentioned, they were about the same height as the boundary layer because thinking was, well, when you go higher up in the boundary layer, and even the free stream velocity is very high. So we want to get a lot of that good flow and pump it into the boundary layer near the surface and re-energize that a lot. So let's make these vortex generators interact with the fluid up there and drag it down. But then they found that there are some benefits to that. So obviously they are very effective in doing that. One problem is, though, that they create a lot more drag. So they create drag not only due to friction, as we'll cover shortly, but also due to an increase in pressure drag, because you now have a lot more vorticity and a lot more wake and chaotic motion. So to get around that, sub-boundary layer vortex generators or micro-vortex generators were also investigated. And there are quite a few papers, which I should actually cover in a podcast because they are very interesting. But they found that micro-vortex generators can perform almost as well as a regular vortex generator, but they don't give nearly as great a drag penalty. So they are very good. And that's one of the ideas of this paper. And we look at 3 different vortex generators. So that's vortex generators in a nutshell. Let's get on with what they investigated and these different types of vortex generators, because you can have more than you can poke a stick out. Like, there are so many different types of vortex generators out there that you can make. And they looked at 3 different ones, one that I've never seen before, and it was quite interesting. So let's get into it. Oh, before going further as well, I should probably say this is quite a big paper as well. And there's a lot to cover in vortex generators. So this will probably be a 2-part podcast. And I'll probably do a lot more podcasts on vortex generators as well, because you can do like 10 or 20 of them and you'll still cover new things every time. There's just that much information on them. So here they say vortex generators are passive flow control devices usually placed in pairs with an array configuration on the blade surface of interest. And the aim of it is to modify the airfoil pressure distribution and delay flow separation, as I mentioned earlier. Let's just quickly cover passive flow control devices. What that means is you don't really have any feedback. You can't, the strict definition is you can't change their shape and there's no feedback. So they're just objects that you place on something and that's how they stay forever. And they are usually placed in pairs. What this means is you can either produce co-rotating vortices or counter-rotating vortices. If you think about what vortices do to a fluid, it entrains and induces velocities in the fluid around it, around a vortex. So if you have 2 vortices and they're rotating in the opposite signs, when you're between 2 of them and they're both rotating such that they're pushing fluid down, the fluid in between them starts to get squashed and the boundary layer becomes actually much thinner. When you go between 2 vortices that are spinning in the opposite sign, but they're pushing the velocity up, the fluid up, so then training the fluid and moving it up, the boundary layer gets much thicker. So those are for counter-rotating vortices. And these are, I don't want to say they're the most popular because I haven't covered every single situation with vortex generators, but I'm going to say they're the most popular because everything that I've really seen, and it's over a bunch of different fields, counter-rotating vortices and counter-rotating vortex generators are usually far more common. Now, co-rotating vortices, on the other hand, these are vortices that spin in the same sign. So it doesn't matter where you go along the span. You have one vortex which is always going to be pushing fluid up, the other vortex which is always pushing fluid down. And just off the top of my head, generally these vortices don't delay stall as well as counter-rotating vortices. So that's what they mean when they say they're placed in pairs. They'll usually operate in pairs in a sort of fashion. And then they say that the local boundary layer is modified by these vortex generators, and there's an exchange of momentum between the upper part of the boundary layer, as I mentioned, and the lower part of the boundary layer. And this modification of the boundary layer is possible due to the incidence angle marked by the angle of attack of the vortex generator to the free stream velocity. So vortex generators are dimensioned with respect to the local boundary layer, as I mentioned, to the boundary layer thickness, I should say. And then as a result, they say that a friction increment is produced by making the boundary layer become more turbulent. So as you'd expect, if you are making the velocity near the surface go faster, it means that the friction is going to increase a little bit. But as I mentioned earlier, that's not the only drag component that does increase. Also, pressure drag often increases as well. But that can be reduced with micro vortex generators or sub-boundary layer vortex generators. Another thing that most people don't talk about is that vortex generators can change the induced drag of the wing. And the reason why they do that is because they change the circulation around the wing. I'm not going to get into that because that was actually a big part of my PhD. And as I mentioned, it's a 4-year project, so I can't really cover much of that in 5 minutes. I'll probably do something else on that later. But they can change the induced drag of a wing based on changing the circulation. I've done some other podcasts talking about circulation as well there. So generally, vortex generators can be set as a counter-rotating array or co-rotating array, as I mentioned. Vortex, and then as I mentioned, they can be put onto many different applications. So they can be on regular airfoils of fixed-wing aircraft. They can be on blades of rotating aircraft, rotating wing aircrafts. They can be on cars. They can be on wind turbines. And in this paper, they want to look at wind turbines. Now, one limitation of this paper is that they didn't, as far as I can tell, they didn't look at the rotational effects of the wind turbine on the fluid. So when a wind turbine goes around, obviously the blades rotate, and that rotation affects the path that the fluid going over the blade will take, and also affect the airfoil profile that the fluid will see. But they want to look at how these voltage generators can be used in a wind turbine situation. They say that these vortex generators could be installed on the blade zones where the flow separation regions exist, thus improving the fatigue limit, the fatigue lifetime of the blade due to reduced load fluctuating, which occurs due to flow separation. So by putting these voltage generators on these blades, they can reduce the amount of flow separation and reduce the fluctuations in loading and increase the lifespan because it's not fatiguing as much, the blade. So vortex generators are easily installed and they can be used as an add-on for wind turbines that do not perform as expected. For instance, due to blade surface imperfections in the manufacturing process. So some studies such as ERIA showed that at normal operating conditions, the power produced of an onshore 1 megawatt wind turbine can be increased by 15 to 25% when you put wind turbine vortex generators on the wind turbine. That's amazing. So what they're saying is a 1 megawatt wind turbine is suffering by about 15 to 25% due to flow separation, and wind vortex generators can benefit that. They can get rid of that problem, at least to some extent. So the experiment on a 2.5 megawatt wind turbine made by Sullivan in his paper or her paper for testing the effects of vortex generators on the power conversion performance presented an increase in 11%. So in other words, vortex generators are really beneficial for wind turbines. They range between 10% and 25% increases for power outputs. And not to mention the increase in lifespan due to reduced fatigue. And we've done podcasts on blade wind turbines as well in the podcasts around 50, 55. So check them out as well. So the design of a vortex generator is a hard task because of the variety of design parameters, such as the device height, length, and shape. But not only that, you can also have nonlinear vortex generators. So you can have curves, you can have them even backwards. Anything that can produce a vortex is technically a vortex generator if you think about it. So you can have any shape you want under the sun, and it will still be a vortex generator. So that's why there's so much research on vortex generators. They also say that the distance between the vortex generators and the location of them on the blade chordwise direction are important factors as well, which is also true, and also how you align them to the flow. So there's just so much to look at. So they say that it was concluded throughout CFD computations on a negligible adverse pressure gradient flat plate that the lower the device height, the lower the vortex strength level, but also the lower drag penalty. So this is a general relationship, which is true, but there are some microvortex generators which still perform just as well as regular vortex generators. So even though they might produce weaker vortices, they do the job just as well in terms of pumping in high momentum flow into the boundary layer near the surface and delaying stall. But they say here, therefore, the vortex generator height influences the vortex formation. So one thing they say is the primary vortex size increases with the device angle in a non-linear way. So that makes sense to some extent when you think about stall as well. Like this is actually quite meta when you think about it. When you have a airfoil which you're trying to delay stall on, so you put these objects on, but if you put them at too high angle attack, then they're going to stall as well. They may not produce as good a vortex. So that's quite interesting. In this paper, they're looking at 3 different shapes. They're looking at a rectangular vortex generator. So this is just effectively think of a flat plate that's just stuck vertically onto a surface. They're looking at a triangular vortex generator. So think of a right angle triangle, and that's pointing into the flow somewhat. It's at an angle of 18 degrees, but approximately to the flow. and then a NACA 0012 airfoil. That's really interesting because I've never seen a NACA 0012 airfoil used as a vortex generator, and I was quite surprised. That's why I took an interest in this paper. The heights of these vortex generators are 5 millimeters, the lengths are 12.5 millimeters, and they're installed at an 18-degree angle of attack to the free stream direction. And they say a single vortex generator has been computed under a symmetrical flow assumption for a Reynolds number of 2,600 based on the boundary layer momentum thickness. Let me just quickly cover what boundary layer momentum thickness means. When we talk about boundary layer thickness, we often just assume that we're talking about the point in the flow in the boundary layer where the velocity is 99% of the free stream direction, free stream velocity. As we get to that point, we then say, okay, that's the thickness of the boundary layer. But that's only based on the velocity. You can also have the momentum thickness, which is based on the momentum of the boundary layer, which takes into account not only velocity but mass. But then there's also other ways that you can quantify a boundary layer thickness. Boundary layer momentum thickness is one of those ways. And it's fairly common for vortex generators to look into this thickness, not just the typical thickness of based on the velocity of 99% free stream direction, free stream velocity, sorry. I have some pictures here. If you want to see them, you can just click the link in the description or look on our YouTube channel for the podcast. So this is interesting here. They said a turbulence level at maximum free stream velocity was 0.5%. Now, the reason why this is interesting, it may just seem like a general tidbit of information, but it is quite important because we're talking about flow separation. And over a surface, an airfoil, for example, the turbulence intensity will affect how the angle of attack that the object will experience stall. And the greater this turbulence intensity, the more turbulent the flow will be, and then the higher angle of attack the object can be pitched at before stall occurs. So for a turbulence level of 0.5%, that's fairly low. So that's a typical wind tunnel turbulence intensity level. And that means that at, I would say, at about a Reynolds number of 300,000 to 500,000, you're going to be starting to get transitional flow, maybe 200,000. But below that, you have a laminar flow approximately. Above that will be turbulent. That's what a turbulence intensity level of 0.5% will yield for a typical flat plate. So they put these vortex generators in a counter-rotating array. As I mentioned earlier, you can have counter-rotating vortices or co-rotating vortices. They put them in the counter-rotating array, so you have two vortices of opposite signs washing down fluid between them, and then when they're both pointing down, and then when they're both pointing up, they upwash the fluid between them. So let's move on, and I just have a quick domain showing that they're normalizing everything to the height of the vortex generator. So the distance downstream, the distance to the side, etc., are all normalized to the height of the vortex generator, which is what they'll be using from now on, h. Okay, so they look at the results. So it's the CFD simulations they did. They've modeled all three vortex generators and all of them have a height of 5 millimeters. And for the experimental measurements, they give the comparison between the CFD and experiments for the three different vortex generators at different distances downstream and also to the side, which is interesting. So when you think about a vortex generator, you don't really think about how the momentum is being pushed into the boundary layer near the surface in terms of span-wise direction. So you might just think, okay, directly behind the vortex generator is doing that. But when you go a little bit further to the side, now the boundary layer is sort of untouched. So one thing that's good with this paper is that they look at the distance to the side of the vortex generator to see how that gets affected. What they found was that when you go downstream by 10 heights of the vortex generator, directly behind the vortex generator, the boundary layer is very affected. But as you go further away, so half a distance between the two vortex generators, so midway, the boundary layer isn't really affected too much at this point. But as you go further downstream, the boundary layer becomes more and more affected at this point. And why is that? Well, that's because the vortices are now dissipating, they're growing, and they're getting weaker in their core, lower vorticity in their core, I should say, they are breaking down, which then leads to their weakness. But because they are getting bigger, they're interacting with a lot more fluid to the side of them. Of the vortex generator, they're covering more distance. So that means that between the vortex generators now, that boundary layer is getting more affected the further downstream you go, until the vortices break down, of course. Another interesting thing to look at is, as you go further to the side, the boundary layer does not follow a continuous pattern, really. I mean, when you look at the boundary layer velocity profile, it sweeps up, but at certain points there are inflections. So, like near the surface, the boundary layer velocity is faster than going up a few millimeters. So that means that the vortices are doing their job, where they're pumping a lot more higher velocity flow into the boundary layer near the surface. But it's just interesting to see this pattern because you don't see it too often. Now, they also look at the triangular vortex generator, the same sort of thing, and they find, again, as you go downstream, the boundary layer gets affected a little bit more to the span-wise direction, but they also are doing their job in terms of pumping a lot more velocity into the boundary layer near the surface. So that's good. So they say, for all studied vortex generators, a deficit in the velocity in zones near the vortex core is observed as a normal behavior. The vortex size is increased downstream of the vein. So let's talk about this. That's interesting. They say the velocity in the zones near the vortex core reduces. And that kind of makes sense, because if you're in the vortex core, you're not actually having any velocity being pumped into it, because there's no upwash or downwash. You're in the core. So technically it's just stagnant, I guess. Or not stagnant, but it's not going up or down or to the sides. But as you go further away from the core, you then have more upwash and downwash. That's when it's going to be more effective. So that's interesting to note. They say for a span-wise location of z equals 0, so the boundary layer is thinned, but for a span-wise location of z equals 10 millimeters, the low momentum fluid is swept upwards by the vortex, thickening the boundary layer and making it less prone to separation. They say that the symmetrical vortex generator of the NACA 0012 show similar velocity profiles compared with the triangular vortex generator ones. So again, as I mentioned, I haven't seen an NACA 0012 vortex generator before, and it just shows you how many different geometries you can come up with. You can literally come up with anything you want, and it will work. Now, one cool thing I have is the cross-sectional velocity planes as you go downstream of the different vortex generators. And it's really cool when you're very close to the vortex generator to begin with. You get typical roll-ups where you have two vortices of opposite signs rolling up. As you go further downstream, they kind of become like mushroom clouds, like, when you drop a nuke and you get the mushroom cloud forming. That's what they look like, and then they start to dissipate from there. So they grow up, they get higher up in the boundary layer, and then they just start dissipating. And in the cores of these vortex generators, or these vortices, sorry, you get a very slow-moving fluid, as you'd expect. Now, the last thing we're going to cover in this podcast before the second podcast is a vortex trajectory. So the vertical path and the lateral path of the primary vortex core downstream of the vein is presented in Figure 10. Let's go to Figure 10. So what they have here are the three different vortex generators and how the vortices from these vortex generators move up downstream. So in a vertical path, up and down, and laterally, left to right. And what they find is the vortices from the NACA 0012 and the triangular vortex generators stay much closer to the surface than for the rectangular vortex generator. Now, this kind of makes sense to some extent, because when you think about the rectangular vortex generator, it's just a block of mass. So the vortex is being produced along the entire thing, whereas for the triangular one, the vortex is really only being produced near the back, because that's where the thickest part is. Now, for the NACA 0012, I forgot to mention what I think it's doing to create a vortex. So I think the way that it's creating a vortex is simply due to the wingtip vortex. You have the NACA 0012 that's installed an angle of attack of 18 degrees. So that's producing a lot of lift. In fact, it's probably going to be stalling, but there should be a bit of lift still. And because you're producing lift, you have a wingtip vortex being produced. And I think it's that wingtip vortex which is acting the same way. I think that's how they're producing the vortex. I'm not sure. If you know, let me know in the comments, but that's what I think it's happening. Okay, so back to the trajectories. As I mentioned, the vortices coming from the rectangular vortex generators they jump up from the surface a lot more, about double actually, to the other vortices from the other two, triangular and negative 12, as you go downstream. In terms of the lateral path, they all follow a fairly similar path in terms of, wandering to the side. They all wander to the side quite a lot as you go downstream. That's why I'm going to end this podcast, because there's still another half of this paper where we talk about vortex decay and strengths and that. That's a very interesting part, and there's a lot to talk about there. That'll be in podcast number 2, the second part. So make sure to like and subscribe this, and check out the Atmosphere Hawk. This is an instrument that we invented to accurately measure the density of the air that you're using in your experiments. The reason why you want to do this is because the density of air changes by 2 to 4% on a regular day, even throughout the day. For example, today, I have my Atmosphere Hawk here actually. When I wake up and I checked it, I took it home with me. I saw that it was about 1.175 kilograms per meter cubed. Now, which is about midday in the office, it's about 1.185. So it's already changed the percent here, and we still have more of the day to go. And this error makes your experiments erroneous, because now when you try to measure the velocity of your wind tunnel, it's going to be different to what you think it's going to be, because the density is different. And then when you try to use that data to validate your CFD, that's a problem, because your CFD, you're assuming a certain density, but it's not. And you're assuming a certain velocity, but it's not that either. So the Atmosphere Hawk gets rid of that error for you, and it makes your experiments much better. So check that out. Link in the description, and I'll see you next podcast. Peace out, amigos.